In this video, we're going to continue with our discussion of magnetism. So we'll be talking about the radius of curvature, Aurora formation, and the magnetic force on a current carrying wire. So if you remember in the previous lecture, we said that a moving charge is going to experience a force when the charge is placed in a region containing a magnetic field. And we said that the force can be calculated using this equation right here. So the force is just the charge times the speed of the charged particle times the strength of the magnetic field times the sine of the angle. So this equation tells me how I can calculate the magnitude of the force. And then the direction of the force is calculated using the right-hand rule. So if this is my velocity vector right here, and this is my magnetic field vector, then notice that if I position my fingers in such a way that my thumb is pointing in the direction of the velocity vector, and my fingers are pointing in the direction of the B vector, then the force is going to be pointing in this direction. Now, before we move on, I want to make a comment about the magnetic field directions. So generally, whenever you see something like that, if you see a small circle with a dot, so the dot simply means that the magnetic field is pointing out of the paper. So it's pointing out of the paper. Now, when you see a small circle with a cross, then this means that the magnetic field is pointing into the paper. So again, this is very useful. So magnetic field pointing out of the paper is a dot. Magnetic field pointing into the paper is represented with a cross. All right, so at this point, let's talk about the motion of a charged particle in a magnetic field. So when a charged particle moves in a magnetic field that is perpendicular to the velocity of the charged particle, the magnetic force is going to cause the particle to move in a circular path. So it's interesting that the speed of the particle is not going to change, only the direction is going to change. So this is an example that tries to explain what is going on. So if you have a negative charged particle here that was moving on a straight line, once it gets into a region that contains a magnetic field, then the magnetic field is going to cause this charged particle to move in a circular path. So in this example, you can see that if this is the direction of the velocity and the magnetic field is pointing into the board, into the paper, then the force is always going to point towards the center right here. So the force is always going to point towards the center of this circle. So we can calculate the centripetal force using this equation right here. So the centripetal force is just the mass of the charged particle times the square of the speed divided by the radius, where the radius is the radius of this circle. Now in this example, because the direction of the velocity vector is at 90 degrees with respect to the direction of the magnetic field, then it means that the angle is 90 degrees. And so since the angle is equal to 90 degrees, the sine of 90 is equal to 1. And so I can calculate the magnetic force on the charged particle using this equation. So it's just given by Q times V times B. So in this case, because the magnetic force is responsible for providing the centripetal force, I can say that this quantity is equal to that, and I can solve this equation to get the radius of curvature, which is given by this equation. So the radius of curvature is just the mass of the particle, the velocity of the particle, divided by the product of the charge times the strength of the B field. All right. So now we're going to look at one example, and this example is example number 22.2. So we're going to calculate the curvature of the path of an electron moving in a magnetic field. And this is an example of a magnet that is placed in front of a TV screen. So what we see here in this picture, so this is the screen, and these are electrons. So these electrons were supposed to be moving in different directions like this. But as soon as those electrons get closer to the magnetic field, so this is the north and this is the south, the magnetic field is going to cause those electrons to move in circles around the magnetic field lines. So for the given example, we're told that the electrons are moving with a velocity of 6.00 times 10 to the 7 meters per second. It also tells us what the strength of the magnetic field is 0.5 Teslas. And so what I want to do is to calculate the radius of the curvature. So we can use this equation that we've derived. So we said that the radius of curvature is just the mass times the velocity divided by charge times the B field. So because we know what the mass of an electron is, we know what the velocity of an electron is, we know what the charge of an electron is, we know what the B field is, I can substitute all these quantities into this equation, and I end up getting a value that is about 0.683 millimeters. So what this indicates is that the electrons are going to be disturbed. So electrons that were supposed to be moving on a straight line and getting into the TV screen in order to form an image, now those electrons are being distorted. So this was an electron that was moving on a straight line, but once it gets into this magnetic field, it just continues to move in an orbit about the direction of the magnetic field line. So you can really see this on this picture right here on the right. So if this is the magnetic field lines pointing in the X direction, then you can see that an electron that was originally moving in the straight line is going to be caused to move in circles in a helical path as shown on this picture. All right. So another application of the magnetic fields that we can imagine is an application that is used in radiation therapy, in the radiation therapy machine. And this is used in the hospital in the production of X-rays. So generally in a hospital, to produce an X-ray, you need to start with electrons. So you generate some electrons here, and then those electrons are going to go through a region here that has a very strong electric field. So the electrons are going to be accelerated by the electric field. And so what you want is that you want those electrons to strike this target. So this is called the target. But for the electrons to get to this target, the electrons would have to go through a region that contains a magnetic field. So this is the initial direction of the velocity. So the electrons are moving on a straight line. Then once it gets into the region that contains the magnetic field is going to bend those electrons to move in a circle until the point where the electrons are going to exit and then start moving in the Y direction to strike the metal, the target. So this is a very important application of magnetism in the production of X-rays in the hospital. So again, electron is moving in the X direction on a straight line. Once it gets into this region that contains a magnetic field, it's going to move in a circle. So you change the direction of the electrons, and then finally the electrons will get to this target right here. So the picture that you see on the right here is a real so this is a real X-ray machine. So this is called an X-ray machine. So it uses a magnetic field to generate X-rays. Now we can also think about another application of the of magnetic fields on moving charges is the production of auroras. So generally what happens is these are like very high energy particles that are called solar storms. Now these particles are energetic particles that are produced out of space. And as those particles move close to the Earth, because the Earth has a very strong magnetic field, the magnetic field is going to cause the particles to move in circles. So the particles get accelerated. And as the particles get accelerated, they can generate electromagnetic radiation in the form of light, and the light could be of different colors. Another application is that when these charged particles are accelerated by the magnetic field of the Earth, the charged particles can also collide with air molecules. And when they collide with air molecules, then it can knock off electrons from the air molecules, so you can ionize the air molecules, and those air molecules can give off light. And the light can be of different colors like blue, green, and yellow. All right, so now we're going to move on to section 22.7. So we're going to look at the magnetic force on a current carrying conductor. So on this picture, what you see here, this is this is my power supply. This is the positive and this is the negative. And this is just a wire that carries a current, and the current has a magnitude I. So when there is a current that is flowing in this wire, once this wire is placed in a region that has a magnetic field, then the magnetic field is going to generate a force on the wire. And again, we can use the right-hand rule to calculate the direction of the force. So in this example here, you can see that the magnetic field is always pointing from north to south, and my current is pointing in this direction. So again, if I use my right-hand rule, so my thumb is placed in the direction of the current, my fingers are placed in the direction of the B field, and then the force is going to be pointing in the upward direction, like shown in this picture. All right. So now we're going to derive an equation that we can use. So we've seen that a charged particle moving in a magnetic field experiences a force. Now, because current flowing in a wire is produced by moving charges inside the wire, a wire would also experience a magnetic force when placed in a magnetic field. And the magnitude of the force can be calculated using this equation. It's F is equal to I times L times B times sine of theta. So in this equation, F is the force that is in newtons, I is the current that is in the wire in amps, L is the length of the wire that is in the magnetic field, and this will be in meters. B is the strength of the magnetic field in Teslas, and theta is the angle between the current and the magnetic field vector. So again, we're going to use this equation to calculate the magnitude of the force, and then we use the right-hand rule to get the direction of the force. So again, if this is the direction of the current and this is the direction of the B field, then the force is going to be pointing up. All right, so now let's look at this one example right here. So suppose I want to calculate the force on a wire as shown on this picture. So it tells us what the strength of the magnetic field is 1.50 Teslas, and the length of the wire is 5.0 centimeters, and it carries a current of 20.0 amps. So in this example, we notice that the magnetic field is at 90 degrees with respect to the current. So when I take the sine of 90, it's just going to be equals to 1. And so if I plug it into this equation, I get a force that is equals to 1.50 newtons.